Hi everyone, welcome to new class. Today's class is about logic gates. Logic gates are the fundamental building blocks of digital systems. The name logic gate is derived from the ability of such a device to make decisions in the sense that it produces one output level when some combinations of input levels are present and a different output level when other combinations of input levels are present. There are three basic types of gates: AND, OR, and NOT. The interconnection of gates to perform a variety of logical operations is called logic design. Inputs and outputs of logic gates can occur only in two levels, and these two levels are termed high and low, or true and false, or on and off, or 1 and 0. A table which lists all the possible combinations of input variables and the corresponding output is called a truth table. Let us study the three gates in detail. First one is the AND gate. An AND gate has two or more inputs, but only one output. The AND gate has two or more inputs, but only one output. The output assumes the logic 1 state only when each of its input is at logic 1 state. That is, the output assumes the logic 1 state only when each of its input is at logic 1 state. And the output assumes the logic 0 state even if one of its input is at logic 0 state. The AND gate may therefore be defined as a device whose output is 1 if and only if all its inputs are 1. Hence, the AND gate is also called an all or nothing gate. And the logic symbol and truth table of two input AND gate is shown here. So this is the logic symbol for two input AND gate. A and B are two inputs and X is the output, and X is equal to AB. That is, it is written as A, B, or A dot B, or A and B. It can be read as A dot B or AB or A and B. So X is equal to A dot B or AB or A and B. So this is the truth table of two input AND gate, and note that the output is 1 only when all the inputs are 1. And in the case of 3 input AND gate, so this is the logic symbol. A, B, C are 3 inputs and X is the output. X is equal to A, B, C, or we can write A dot B dot C, and this can be read as A and B and C, or A dot B dot C, or simply ABC. And the 3 inputs are 0, 0, 0. That is, in the case of 2 input AND gate. The combinations of inputs are 0 0 0 1 1 0 1 1 and the output is high only when all the inputs are high. That is 1 1 only. The output is 1 if the inputs are 1. That is 1 1 is output is 1 and all the outputs are 0 when on any of the input is 0, the output is 0. And in the case of 3 input AND gate, the combinations of inputs are 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 and the output is 1 when all the inputs are 1. That is 1 1 1. When the inputs are 1 1 1, the output is 1. And when any of the input is a 0, the output is 0. So this is the case of 3 input AND gate. Next is the OR gate. The OR gate may have 2 or more inputs but only one output. And here the output assumes the logic 1 state even if one of its input is in logic 1 state. That is, this is the truth table of 2 input OR gate. The output assumes the logic 1 state even if any one of the input is in logic 1 state, and its output assumes the logic 0 state only when each one of its inputs is in logic 0 state. So an OR gate is defined as a device whose output is 1 even if one of its input is 1. Hence, an OR gate is also called an any or all gate. So this is the logic symbol of 2 input OR gate and this is the truth table, and these are the input combinations, that is 0 0 0 1 1 0 1 1 and the output is high if any of the input is high, that is 0 if all the inputs are 0, that is 0 0, then the output is 0 and in all other cases the output is 1. And here the inputs are represented as A and B and the output is x equal to A plus B. It can be read as A plus B or A or B. A plus B or A or B. That is x is equal to A plus B, or we can read as x is equal to A or B. And the symbol of the logic symbol of 3 input OR gate is, it is like this. That is, this is the OR gate. 3 input OR gate is A, B, C and one output, that is x is equal to A plus B plus C. So this is the logic symbol of 3 input OR gate. And the truth table is inputs, output, then A, B, C, one output. That is, the combinations are 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So the output is 0 when all the inputs are 0 and in all other cases the output is 1. So this is the truth table of 3 input OR gate and this is the logic symbol. Next is the NOT gate. A NOT gate, also called an inverter, has only one input and only one output. This the symbol of NOT gate is like this. The input is A, output is X, and X is equal to A bar. It is read as X is equal to A bar. So this is the logic symbol of a NOT gate. And the truth table. Truth table, only one input and one output. That is, when the input is a 0, the output will be its complement. That is, the output of a NOT gate will be the complement of the input. That is, when the input is 0, output will be 1, and when input is a 1, output will be 0. So this is the case of NOT gate. That is, the output of a NOT gate assumes logic 1 state when its input is in logic 0 state and vice versa. Next is the universal gates. Though the logic circuits of any complexity can be realized by using only the three basic gates and or inverter or and or NOT gates, there are two universal gates, NAND and NOR gates, each of which can also realize the logic circuit single-handedly. The NAND and NOR gates are also therefore called universal building blocks. Both the NAND and NOR gates can perform all the three basic logic functions and, or, and not. Therefore, this AOI logic can be converted to NAND and NOR logic. Next is the NAND gate. NAND means not AND, that is, the AND output is noted. So, a NAND gate is a combination of AND and NOT gate, that is, AND gate, then a NOT gate. That is, this is the inputs A, B, then the output of AND gate is A, B or A dot B or A and B. Then the output here is X is equal to A, B whole bar. It is read as X is equal to AB whole bar, or we can say A dot B whole bar, like that. And the symbol of two input NAND gate is, this can be like this, that is, this is two input NAND gate. This is the symbol A, B, and X is equal to A, B whole bar. So this is the logic symbol of two input NAND gate. And truth table is inputs, output, then A, B. A, B are here, A, B are the inputs, and output is X. The combinations of inputs are 0, 0, 0, 1, 1, 0, 1, 1. And here the output is logic 0 only when each of the input assumes a logic 1 level. That is, here when both the inputs are high, that is A and B are high, that means x is equal to 1 dot 1. 1 dot 1 is 1 and 1 bar, that is 1 complement is 0. So the output is logic 0 level only when each of the input assumes a logic 1 level. For any other combination of input, the output is a logic 1 level. These are 1. That is, here output is x is equal to a dot b whole bar. So when both the inputs are 0, then we will get 0 dot 0. 0 dot 0 is 0 and complement of that 0 is 1. Next input is 0 and 1, that is 0 dot 1. Then 0 dot 1 is 0 and complement of that is again 1. Then 1 dot 0 also 0. Then complement of that 0 is 1. So this is the case of 2 input NAND gate. And similarly in the case of 3 input NAND gate, the symbol is 3 input. It is A, B, C. Output here noted, that is x is equal to A, B, C the whole bar. So this is the logic symbol of 3 input NAND gate. And in the truth table, this is the truth table of 3 input NAND gate. So here also the output is logic 0 level when each of the input assumes a logic 1 level, and all other cases the output is logic high. And the NAND gate can perform the OR function. That is, the output x is equal to a b whole bar can be written as a bar plus b bar. This is the OR operation of NAND gate. That is, x is equal to ab the whole bar is equal to a bar plus b bar, or a complement plus b complement. That is, a NAND function can be realized by first inverting the inputs and then ORing the inverted inputs. Thus, a NAND gate is a combination of two NOT gates and an OR gate. So we can draw it like this. That is, first inverting the inputs, then OR its output. That is, this is the OR gate. Then we will get x is equal to, this is a bar, this is b bar. Then we will get a bar plus b bar. And it can be drawn like this. That is a b. And here the output x is equal to a complement or a bar plus b bar. And this is called the bubbled OR gate. This is called the bubbled OR gate. And its truth table can be drawn like this. It is here inputs, then inverted inputs, then output. That is AB. This one AB. Then inverted output, inverted input to this OR gate is A bar, B bar. Then output is X. That is A and B combinations are 0, 0, 0, 1. Then 1, 0, 1, 1. And here A complement, that is 0, 0. Here becomes 0 complement is 1. Then B complement 1. Here 0, 1, 1, 0. Then here 1 is 0. Then 0 complement 1. Here 1, 1. Then 0, 0. Now or this inputs, that is A complement plus B complement, x is equal to A bar plus B bar. That is here in the case of OR gate, the output is high when any of the inputs are high. So we'll get the output as 1, 1, 1, 0. So it is same as the truth table of NAND gate. So the NAND gate is, otherwise we can say that it is a bubbled OR gate. Next is the NOR gate. NOR means not OR. That is, the OR output is noted. So a NOR gate is a combination of an OR gate and a NOT gate. And the logic symbol can be drawn like this. So this is OR gate and its output is noted. These are inputs A, B. Here it will be A plus B or A or B. Then the output x is equal to A plus B the whole bar. And the logic symbol of NOR gate is like this. That is 2 input A plus B the whole bar, x is equal to 2 input or NOR gate. So this is the logic symbol of 2 input NOR gate. And the truth table inputs, output, then A, B, X. The combinations of inputs are 0, 0, 0, 1, 1, 0, 1, 1. And here the output is logic 1 level only when each of its inputs assumes a logic 0 level. That is, here when both the inputs are 0, that is 0 plus 0 is 0, then its complement is 1. And any other combination of inputs, the output is logic 0 level. That is, here x is equal to A plus B the whole bar. Then when A and B are 0, 0, it will become 0 plus 0 the whole bar, that is 1. When it is 0 and 1, then 0 plus 1, that is 1. Then 1 bar is 0. Then 1, 0. 1 plus 0 whole bar, that is again 0. Then when it will become 1, 1, that is 1 plus 1 the whole bar. 1 plus 1 is 1 and its complement is 0. So this is the case of 2 input NOR gate, and it is same as for the 3 input NOR gate. That is 3 input NOR gate. The symbol is like this, that is A, B, C, and the output is x is equal to A plus B plus C the whole bar. And here also the output is a logic high or logic 1 when all the inputs are 0 and output is 0 in all other cases. So this is the truth table of 3 input NOR gate and this is the logic symbol. So here when all the inputs are 0, the output is high, and when and in all other cases the output is 0. And the NOR function can be realized by first inverting the input and then ANDing the inverted input, that is x is equal to a plus b whole bar, and this can be written as a bar dot b bar. That is first inverting the input and then ANDing the inverted inputs. That is, a NOR gate is a combination of two NOT gates and an AND gate. That is, we can draw like this, two NOT gates and AND gate. So these are the inputs A, B. Here this is A bar, this is B bar, and the output X is equal to A bar into B bar. And this can be drawn like this, that is A, B, and the output X is equal to A bar into B bar. And this is called the bubbled AND gate. That is, the NOR gate can be drawn like this, that is bubbled AND gate. The AND gate with inverted input is called bubbled AND gate. So a NOR gate is equivalent to a bubbled AND gate, and its truth table is inputs, the inverted inputs, then output. Inputs are A, B, then inverted inputs A bar, B bar, output is X, 0, 0, 0, 1, 1, 0, 1, 1 are the combinations of inputs. Then here it will become 1, 1, then A bar here 1, 0, then here 0, 1, then 1, 1 will become 0, 0. Now output X is equal to A bar in A bar dot B bar, that is 1 dot 1. 1 dot 1 is 1, and that is here it is 1. 1 dot 1 is 1. Here 1 dot 0 is 0. 0 dot 1 is 0. 0 dot 0 is 0. So this NOR gate is equivalent to a bubbled AND gate. Next is the exclusive OR or XOR gate. An XOR gate is a two input one output logic circuit whose output assumes a logic 1 state when one of its two input assumes a logic 1 state. Under the conditions when both the input assume the logic 0 state or when both the input assume the logic 1 state, the output assumes a logic 0 state. The logic symbol of an XOR gate can be drawn like this. That is X is equal to A XOR B. So this is the logic symbol of XOR gate, and it can be read like this, that is X is equal to A XOR B, and the truth table is inputs, output, then A, B, here X, 0, 0, 0, 1, 1, 0, 1, 1. So The output assumes a logic 1 state when any of the two input assumes a logic 1. That is, these are 1, and when both the inputs are 0 or both the inputs are 1, the output is 0. That is, x is equal to a XOR b, and we can written as a b bar plus a bar b. So this is the XOR gate. A b bar plus a bar b. Since the XOR gate produces an output 1 only when the inputs are not equal, it is called anti-coincidence gate or inequality detector. Anti-coincidence gate or inequality detector. And XOR gate as an inverter. XOR gate can be used as inverter, that is, when one of the input is 1, then it will act as inverter, that is input bar. So when one of the input of the XOR gate is a high or logic 1 state, we will get the output of the XOR gate as inverted. The name exclusive OR is derived from the fact that its output is a 1 only when exclusively one of its input is a 1, or we can say it excludes the condition when both the inputs are 1. Next is the exclusive NOR gate or XNOR gate. An XNOR gate is a combination of an XOR gate and a NOT gate. That is, the symbol of exclusive NOR or XNOR gate is combination of XOR gate and NOT gate. That is, A, B, output is X is equal to A XNOR. This symbol is XNOR. A XNOR B. This is the logic symbol of XNOR gate. And the truth table is inputs, output, then A, B, X, 0, 0, 0, 1, 1, 0, 1, 1. Output is 1, 0, 0, 1. The XNOR gate is a 2 input 1 output logic circuit whose output assumes a logic 1 state only when both the inputs assume a 0 state or when both the input assume a 1 state. It is also called a coincidence gate because its output is 1 only when its inputs coincide. It can be used as an equality detector. Because its output A1 only when its inputs are equal. The output can be written as X is equal to A XNOR B, and that is equal to A dot B plus A bar dot B bar, or we can write like this: A XOR B the whole bar, or A B bar plus A bar B the whole bar. XNOR gate can be used as an inverter by connecting one of the two input terminals to logic 0. That is, by connecting one of the two input to the logic 0, we will get the input inverted. That is, the XNOR gate can be used as an inverter by connecting one of the two input terminals to logic 0. Then we will get the input inverted. And remember, XNOR gate is complement of the XOR gate. Thank you for watching the class. If you like the classes, please like, share with your friends and subscribe my channel.